Hello everyone. In this episode, I'll introduce tropical cyclone observations. Tropical cyclones generally form over tropical oceans. According to statistics, an average of about 80 tropical cyclones form globally every year. Their formation regions can be divided into 7 ocean basins, which are mainly distributed between the 5th and 20th degree latitude in both the northern and southern hemispheres. Among them, the number of tropical cyclones forming over the western North Pacific is the highest, with an average of about 30 every year. This contributes to around 40% of the total number. This is because the western Pacific has a broader area of warm sea surface. Whereas the relatively low sea temperature over the South Atlantic Ocean makes it unfavorable for the development of tropical cyclones. However, there were still formation records of tropical cyclones in the past over there. According to past scientific studies, there are generally 6 conditions to be fulfilled for the formation of tropical cyclones. First, the sea surface temperature needs to be above 26 degrees Celsius. This temperature is related to the thermal properties of the atmosphere in tropical regions. Sea surface temperatures must reach this level or above for the initiation of deep convection. Second, there must be sufficient water vapor from the lower to the middle levels of the atmosphere. Third, an unstable atmosphere is required to facilitate the development of deep convection. Fourth, it has to be located at suitable latitudes. The latitudes for tropical cyclone formation in general need to be 5 degrees or above away from the equator. The Coriolis force due to the Earth's rotation increases with latitude. As the Coriolis force near the equator is too small for the generation of vortices, tropical cyclones can hardly form there. Fifth, the vertical wind shear, that is, the change in wind direction or speed between the lower and upper levels of the atmosphere, cannot be too large, because strong vertical wind shear can disrupt convective activities. Last, there must exist a cyclonic vorticity, or convergence of air streams in the low level of the atmosphere. In addition, the upper-level divergence can facilitate convective activities, thereby favorable for tropical cyclone formation. However, this isn't a necessary condition for the formation of tropical cyclones. Sometimes, even if some conditions are not fully satisfied, but when other conditions are rather favorable, a tropical cyclone can still have a chance to form. The basic condition for tropical cyclone formation is the convergence of airstreams in the lower atmosphere. One of the favorable locations for cyclone generation is the intertropical convergence zone. It's a belt of low pressure located near the equator, which moves periodically in a meridional direction every year. The section of the intertropical convergence zone extending from the South China Sea to the western Pacific is also called the monsoon trough. It's formed by the convergence of the southwest monsoon crossing the equator from the southern to the northern hemisphere and the northeasterly trade winds at the southern periphery of the subtropical ridge in the northern hemisphere. The convergence of airstreams in the monsoon trough is favorable to the development of convective activities and provides a vortical wind field. Most of the tropical cyclones in the western North Pacific form there. We can see from the structure of the tropical cyclone that airstreams in the lower atmosphere of the northern hemisphere rotate anti-clockwise and flow inwards to the center of the tropical cyclone. Meanwhile, there are multiple narrow and elongated spiral rain bands caused by strong updrafts. These rain bands generally bring heavy squally showers. When these airstreams rise to the upper atmosphere, they'll flow outwards in a clockwise direction called outflows and form a dense cirrus overcast. Airstreams subside at the outer circulation of a tropical cyclone, which can bring very hot weather to those regions. The center of a tropical cyclone is also characterized by subsidence of air, which forms an eye with low cloud amount and light winds. The eye is surrounded by the eye wall, which is the region of maximum wind speed in the whole tropical cyclone. From satellite images, we can see that a mature tropical cyclone usually has obvious spiral cloud bands as well as a clear eye. Sometimes we can even see the structure of the eye wall. Methods of tropical cyclone observations mainly include the following: satellite imageries, radar data, surface observations, and aircraft observations. Due to the lack of direct observations near the sea surface over vast oceans, satellites have become a very useful tool for observing tropical cyclones, especially for determining their location and intensity. If the eye is clearly visible, the position of its center represents the center of a tropical cyclone. If an eye is invisible, a closer look of the shape and movement of the spiral cloud bands is required, especially the movement of the low clouds, in order to locate the center of a tropical cyclone. There are also cases when a weaker tropical cyclone is located in an environment with stronger vertical wind shear, where the convective clouds of the tropical cyclone are blown far away from the center, leaving an exposed low-level circulation center. In daytime, we can make use of visible satellite images to deduce the center location, based on the features of cumulus's cloud lines. In nighttime, it's more difficult to determine the location because the low-level cloud lines are hardly visible from the infrared satellite images. In these cases, we can sometimes use microwave imageries from satellites to better deduce the tropical cyclone's center location. The Dvorak analysis technique is a statistical method for estimating the intensity of tropical cyclones based on their features on satellite images. It's mainly based on the shapes of spiral cloud bands, cloud temperatures, etc., in addition with the use of integrated flowcharts to determine the intensity of tropical cyclones. This technique is commonly used by tropical cyclone forecasting centers around the world. However, different regions may have slight discrepancies in the intensity estimation of tropical cyclones with similar features. Apart from satellites, radars are also very useful in observing tropical cyclones. Compared with cloud observation of tropical cyclones via satellites, radar can capture the rain bands of tropical cyclones. If a tropical cyclone enters within the monitoring range of a radar, its center location and intensity can be estimated based on the radar data. In general, a mature tropical cyclone can be observed as having a well-formed circular eye, and its location is the center of the eye. Weaker tropical cyclones may not have visible eyes. In these cases, we need to carefully study the shape of spiral rain bands and the movement of radar echoes to estimate the tropical cyclone's center location. The Doppler weather radar is used to assess the intensity of tropical cyclones. It can measure the approaching or departing speed of raindrops, which is the radial speed. Moreover, the moving speed of raindrops very much reflects the wind speed at that location. We only need to use some simple formulas to calculate the surface wind speed from the radial velocity of raindrops in order to assess the intensity of the tropical cyclones. In addition, there is a white line called zero isodop between the raindrops moving towards and away from the radar. The center of a tropical cyclone should lie on the zero isodop. Land-based weather stations, ships and buoys, etc. provide important surface observation data to assist the analysis of location and wind field of tropical cyclones. The data from these observation stations will be shown on weather charts. Forecasters can analyze the distribution of wind direction and speed in various regions. In the most ideal situation, if there are 3 wind stations in the vicinity of a tropical cyclone, we can use the inflow angle method to calculate the center location of the tropical cyclone. In addition, surface observing stations also provide wind speed data directly that can be used as references for estimating the intensity of tropical cyclones. However, due to geographical limitations, these observing stations are rarely able to capture the maximum wind speed or the minimum air pressure near a tropical cyclone center. The Hong Kong Observatory has been in close collaboration with the Government Flying Service over the years to arrange fixed-wing aircraft to collect meteorological data over the sea areas near Hong Kong when necessary. It can collect meteorological data at different altitudes in the atmosphere to complement the lack of weather observations over the ocean. It's especially useful in determining the location of tropical cyclones and analyzing their intensity. When Typhoon Vicente approached Hong Kong in 2012, aircraft observations provided valuable data to assist in position fixing. When Tropical Cyclone Lin Fa approached the coast of Guangdong in 2015, Through aircraft observations, forecasters could timely identify that the wind speed near sea level close to the eye had reached hurricane force, and also conducted more detailed analysis of the spatial coverage of gale and storm force winds. Since 2017, the dropson system has been used to detect the three-dimensional structure of tropical cyclones. These data are valuable for determining the location and intensity of tropical cyclones. Okay, in the next episode, I'll introduce the forecasting techniques for tropical cyclones to you. Goodbye.